we need to derive the reaction force at, for example, the fixed support at wall. So the vertical reaction force at wall is RL, and the moment reaction force at wall is MW. So it also provides reaction force. The free body diagram is shown here. So we have two reaction force over on the left hand side of this beam, and right hand side we have one reaction force RR and applied moment M. So look at here, it's a fixed at wall, so it's a fixed support. If we say this support is A, okay, as we know, the fixed support have three reaction force. So, but here only have two reaction force. What's the reason? So if we put a three reaction force is AX over here. AX is the horizontal reaction force. RL is a vertical reaction force, and MW is the reaction moment. So if we write down the equation of equilibrium in horizontal direction, so horizontally we can only find one reaction force, that is AX. So AX must equal to 0. Okay, so because AX equals 0, so in these free body diagrams, it doesn't show the AX here, so we can delete here. So AX equals 0. So from this is a free body diagram with reaction force. So look at this beam. We know this beam is an indeterminate beam to the first degree because we have four unknown force, four reaction force at the support A, one reaction force at the support. So if we say the support B, so four reaction force, but we only have three equation of equilibrium. So it's the indeterminate beam to the first degree. So for this indeterminate beam, we can using fourth method to solve it. So how to use fourth method? So this beam, we can remove the reaction force at the restraint at support B. Then this beam can be divided into two structures. So one structure is here. We have support A, support B, and support B. We have applied moment M. So this is fourth structure. We call this primary structure. So this the second is that if we remove the restraint of support B, we must apply reaction force on support B. If we say the reaction force is By, so we simplify or reduce this indeterminate beam structure into two parts. One is cantilever beam with a applied moment M. The second is a cantilever beam with a reaction force By to the roller support B. So look at these two structures. We can draw the deformation shape. So if we draw the deformation shape, and here we have displacement at the support B is, we say, delta B, and if we draw the deformation shape, we have delta B prime. Okay, so the delta B prime can be expressed by By times Fb. So Fb is a flexibility coefficient. So how to derive flexibility coefficient Fb is we can just this beam we apply 1. We put a unit node 1. So after we apply a unit node, the deflection shape, we will know the displacement is Fb. So Fb is coefficient, the flexibility coefficient. So because the orange structures at support B, there is no displacement. The displacement here is equal to 0. So after we combine these two structures, we must make sure that delta B plus delta B prime equals 0. So then we can make sure that these two structures combined together can return to the original structure. So we know delta B prime is equal to By times Fb. So we will have delta B plus By times Fb equal to 0. So this is the equation we call compatibility equation. So this compatibility equation. From this compatibility equation, we can solve by. We can solve by. So how to solve by? First of all, we need to know the result of delta b and the value of fb. So how to get the delta b? Delta b is shown here. So how to get that? If we're using the virtual worker method, so now we need to solve delta b. And by using the virtual worker method, we need, first of all, we need to build up the real system. So for the real systems, the free body diagram is shown here. We have M, okay? The virtual system to calculate delta B is net, because delta B is shown here is go upwards. So we apply a virtual load 1, go upward. So for real system and virtual system, if we want to using virtual worker method, we can write down the equation that delta B is equal to 0 to L, small m, this is virtual internal bending moment, capital M over EI. So capital M is the real internal bending moment, dx. So we need to know the small m and capital M. This is the bending moment diagram. So we need to draw the bending moment diagram. So if we draw the bending moment diagram, we will find the bending moment diagram like this. So is the value is m, and for this one is L. Okay, this is the bending moment diagram. So as we know, after we know the bending moment diagram, we can apply the visual integration. So to solve it, so the visual integration, so we have the table. One bending moment diagram is shown here is a rectangular. The other bending moment diagram is a triangular. So the expression for these integrals is 1 over 2 m1 m3 times L. So m1 is the maximum magnitude of this bending moment. M3 is the maximum magnitude of this bending moment shown here. So after we know this, we can using visual integration to evaluate these integrals. We will have, if we put EI outside of these integrals, 0 to L m capital M dx, apply the visual integration, we know is 1 over 2 times m times L times L. So this is based on visual integration. We got the result is 2EI m L squared. So we got the delta B. Then we need to we need to find out the value of FB. For FB, we can, so FB is shown here. FB is the displacement and the unit node 1. So to solve this, first we'll build up real systems. The real system is shown here. We have a unit node 1 and a virtual system. So we need to know FB. So we build FB's go upwards. We apply a virtual load 1. So then we need to draw the bending moment diagram. Bending moment diagram is L. Okay. So look at these three systems. So these three systems are same to each other, but they have different meaning. So for this one is a virtual system for the calculation of delta B. But for this one is a real system for the FB, but this one is a virtual system for FB. Although they look the same, but they have different meaning. Okay, so once we know this bending moment diagram, and we can apply a virtual integration method, not a virtual, visual integration method, we find we have a triangle over here, a triangle over here, so the result will be 1 over 3, M1, M3, and L. Okay, once I got this, we can evaluate the FB. So FB equal to 0 to L, small m, capital M, EI dx. We put EI outside of the integrals, 1 over EI, 1 over 3, M1, M3, and times L. We got a result is 3EI L cubed. So this is FB. So we know the delta B, we know FB, then we can evaluate BY. So BY equal to negative delta B over FB. Because result will be delta B will be ml square 2ei times 3ei L cubed. Got result, so this terms negative 2L 3M. So this is BY. So after we load the BY, so BY is a reaction force at the support B. So here we show the reaction force is RR. So this RR equal to negative 3M to 2L. So this negative is that. So here we have a negative. That means we assume the BY is go upwards. So it's negative. That means BY is going downward. But here the R and R is going downward. So we don't need negative over here. So once we know the R and R, we can solve this RL and MW just based on the two equations of equilibrium. So if we write down equation of equilibrium in Fy equal to 0 in vertical direction, we can easily find out that RL, so RL is equal to RR. So RL equal to RR equal to 3M over 2L. If we write down the equation of equilibrium, suppose we write down the moment equation of equilibrium in support A. So if we say here's support A, if we write moment equation of equilibrium on support A, we will have, so assume the positive direction go to counterclockwise, we'll have MW plus, so we have MW over here, we have M, we have RR, have bending moment at the support A. So they can express over here negative RR times L equal to 0. And R to R, so we have this value, we plug in R to R, we will have, so let's plug in RR, we got 3M over 2L. So if we cancel L to L, then we got MW equal to 1 M over 2. So this is the result. MW, this is RL. So we know in this question, I already provide the M value is 25 kilonewton meter. L is 5.8 meter. So we plug in these two values, and we got RL. So RL equal to 3 times 25 over 2 times 5.8 kilonewton. And we got a result will be, after we using the calculator, we got a result will be 6.47 kilonewton. For this, M is 25 kilonewton, this 2 is 12.5 kilonewton meter. Okay, so this is the solution by using the force method to solve the reaction force RL and reaction moment MW. That's all.